Pulse modulation is a technique used to encode analog signals for digital communication system. It involves two main steps, sampling the signal and also quantizing it into discrete levels. There are four key types of pulse modulation. The first one is PAM, pulse amplitude modulation, PWM, pulse rate modulation, PPM, pulse position modulation, and the last one is PCM, pulse code modulation. These methods play a crucial role in digital communication by converting continuous analog signals into forms that are suitable for processing, storage, and transmission. Now, let's discuss sampling. Sampling is the process of converting a continuous signal into discrete values by measuring it at regular intervals. The Nyquist theorem is critical here, stating that the sampling rate must be at least twice the maximum frequency of the signal. This ensures accurate representation and avoids aliasing, a distortion that occurs when the sampling rate is too low. Accurate sampling is the foundation for effective pulse modulation. Next, let's move to quantization. Quantization converts the sample values into discrete levels for digital representation. The number of levels is determined by L equals to 2 power of n, where n is the number of bit used. However, quantization introduces noise because the continuous signal values are rounded off to the nearest level. For instance, in 3-bit quantization, there are 8 discrete levels, meaning the signal resolution is limited to those levels. There are two types of quantization. The first one is uniform quantization. The signal is divided into equal step size or levels. It is simple to implement but less effective for signals with significant amplitude variations. An example is an 8-bit PCM systems with 256 levels. The second one is non-uniform quantization. Here, step size vary, make it more efficient for signals with large dynamic range. Common examples include mu-law and A-law algorithm used in telephony, which prioritize smaller steps for weaker signals. Non-uniform quantization provides better signals to noise ratio for signals with varying amplitudes, making it essential for applications like audio compressors.
Have you ever wondered how a recording device captures sound? Let's think about this for a moment. Imagine you are recording music. How precisely do you think the recording device can measure the loudness of the sound at any given moment? What might happen if the device can only measure a few levels of loudness versus this many precision levels? Is determined by something called bit depth in audio recording. Here's how it works. At 8-bit depth, it can capture 256 levels of loudness. And with 16-bit depth, which is the standard for CDs, it can capture an impressive 65,536 levels of loudness. More levels of loudness means smoother and more detailed sound, especially in the quieter parts of a recording. That's why higher bit depths are perfect in professional audio. For instance, 24-bit depth used in studio recordings can capture over 16 million levels of loudness. And of course, there's a trade-off. Higher bit depth demand more storage space for the audio file, but the improvement in sound quality is so worth it for music producers. Bit depth determines how many different amplitude values we can capture for each audio sample. This is also known as the level of the sample. Essentially, bit depth defines the number of possible discrete amplitude values we can use for each sample. The higher the bit depth, the more values are available, which means greater detail and accuracy in the recording. In simpler terms, higher bit depth allows us to capture more of the nuances in a sound. So if you're recording music or any dynamic audio, higher bit depth ensures a richer and more detailed recording.
Let's imagine. Picture this. A busy waiter in a bustling restaurant. The waiter has to serve multiple tables, but they can only handle one task at a time. So how does the waiter manage to serve everyone efficiently? In time division multiplexing, the waiter uses a strategy where they serve each table one by one. The waiter spends a fixed amount of time at each table before moving to the next. This way, every table gets attention in a specific time slot. In frequency division multiplexing, the waiter is a bit like a multitasker. They manage different courses at the same time. For example, they might serve appetizers to one table, the main dish to another, and dessert to third, all happening in the same time frame. Just like the waiter efficiently manage multiple tables, multiplexing helps share a communication channel to handle multiple signals or data streams. Process of transmitting two or more signals simultaneously is known as multiplexing. The main objective of this system is to increase the capacity of a transmission channel. It's a technique that allows multiple signals to share the same communication channel, but each signal uses a different frequency band. This means each signal has its own range of frequencies, which keeps them from interfering with each other. And how it works. First, assigned frequency bands. The communication channel is divided into separate frequency bands. Each signal it gets its own unique frequency band. Second, modulation. Each signal is modulated with its assigned frequency. This means each signal is shifted to its specific frequency band before transmission. And then simultaneous transmission. All signals are transmitted at the same time but on different frequency bands, allowing them to coexist without interfering with each other. And then lastly, demultiplexing at the receiver. At the receiver's end, each signal is separated based on its frequency band and demodulated to retrieve the original data. And then a great example of FDM is radio stations. Each radio station is assigned a specific frequency, such as 98.1 FM or 102.5 FM. All these stations broadcast their signals at the same time, but because they use different frequencies, there's no interference. When you tune your radio to a specific frequency like 98.1 FM, the radio filters out all the other stations, allowing you to hear just that one station. So FDM is widely used in applications like radio broadcasting and television transmissions because it allows multiple signals to be sent simultaneously without interfering with one another, making efficient use for every technique that allows multiple signals to share a single communication channel by dividing the transmission time into fixed intervals called time slots. Each signal is assigned a specific time slot to transmit its data one at a time. And then how it works. First, divide time into slots. The available transmission times is divided into small, fixed-time intervals called time slots. Each signal gets its own time slot. And then sequential transmission. Signals are transmitted one by one in their assigned time slots. Even though it looks like the signals are being sent simultaneously, they are actually being sent in quick succession. And then synchronization. To make sure each signal gets its turn, the system must stay synchronized. This ensures each signal transmits in its correct time slots. And then lastly, reassembly at the receiver. At the receiving end, the signals are collected, reassembled in the correct order to retrieve the original data. And then the example for TDM is digital telephony. In digital phone systems, a single telephone line can carry multiple voice calls. Each call is assigned a unique time slot, and the time slots repeat in cycles. This allows each call to send small chunk of voice data in its turn. Even though multiple calls are transmitted on the same line, each one gets its own time slot, ensuring clear. So this is the advantages of multiplexing, which is efficient use of resources, cost-effective, reduce interference, and lastly, enable advanced technologies. And what we can understand here that multiplexing is a powerful technique that optimizes resource utilization, significantly reducing the need for additional infrastructure while enabling the simultaneous transmission of multiple signals over a shared medium.
Recent advancement in digital communication led fidelity technology that known as Wi-Fi. It is a high-speed wireless communication network similar to the Wi-Fi that provide bidirectional data transfer. The Wi-Fi works on the principle of visible light communication that use visible spectrum as well as ultraviolet infrared radiation. It allows the data to be transferred by modulating the intensity of the light, then received by the photosensitive detector. The light signal is then modulated into the electronic form. The modulation of intensity of light is so fast it cannot be perceived by the human eye and can appear as constant to the human. It is 100 times faster than Wi-Fi and it can provide speed up to 224 gigabytes. Misconception part. Wi-Fi technology, unlike Wi-Fi or 5G, operate using visible light instead of radio frequency signal, placing it in the non-ionizing spectrum of the electromagnetic radiation, meaning it lacks the energy to harm biological tissue. Peer-reviewed studies confirm that visible light is inherently safer when used within the standard limit, similar to everyday LED lighting. To address concerns, we emphasize transparent communication by sharing data on the Wi-Fi operation within safety parameters and highlighting its benefits, such as the absence of RF interference, making it ideal for sensitive environments like hospital. Wi-Fi is a secure, efficient, and a scientifically proven safe technology that boosts innovation without
For the
compromising health.
conclusions, we have covered key topics such as pulse modulation, bit depth, and multiplexing, which are essential for modern digital communication. We also discussed recent advancement in the field and clarified some common misconceptions. Thank you for watching. We hope you gain valuable knowledge and insight from this presentation.